Good morning, everybody. So my name is Justin Warner. I'm a technical director at a small little startup in Seattle called Iceberg. I kind of focus on threat research and detection. Spent a lot of time digging through packets, being a network nerd. Spent a couple years in the Air Force. Never got stationed in Hawaii, unfortunately. Spent all my time at an Army base. And then I did some years of red teaming, which is where I got a lot of inspiration of the work I do now, basically breaking into companies and large Fortune 100 organizations. I have a beautiful wife and young daughter. They're back home. They weren't able to come along. Unfortunately, she had to work as well. This is Alex. He did a lot of research with me on this, so kind of giving him a shout out. He wasn't able to make it today. He's a security engineer on our team, intern turned engineer. So young guy in the field, but just brilliant in terms of packet space. Quick story to hopefully lighten up the crowd. I arrived on Monday. I was all excited. Normally when I come here with my wife, she's from Oahu. I get to do no tourist stuff because it's all like local life, restaurants, family, in-laws. So I got to come out here by myself. I lined up a whole slew of activities. I'm going to hit every hike I've ever wanted to hike, and I'm going to take a ride in a helicopter and all these things. I wish I would have done that after this talk because my legs are dead, but I was able to get some very good views. So just know as I strut around up here, I'm feeling the pain. I want to give a special shout out to all the people who influenced this presentation. Research nowadays is pretty much never original. You're always learning from somebody, whether it's a threat actor or others in the space. So I want to give a call out to all these folks who really kind of gave me the inspiration. They did a lot of the offensive work that led to this research. So let's start with a story. So why are we here? What is this talk going to be all about? Well, first it's the 90s. We had to go back a bit. There are these really cool movies, things like Hackers, old computers that some people might not even recognize depending on how old you are. Windows 3.1, Windows 95, we start progressing, getting better GUIs. Funny books with dogs on them called Decom. Don't know why they chose dogs, but it's a great cover. This is actually the book I read to learn this material. It's a fantastic book. And then we progress to modern day when Decom is no longer just a protocol that's being used, it's being abused. So there's people like Matt Nelson, goes by Enigma, writing a whole bunch of blog posts on how attackers can use this protocol. Great post by Cyber over detailing all of this. Another post, again, just continuing to be abused by attackers. It's been covered by MITRE ATT&CK. It's a well-known technique. It's been used by APT33 and a couple of the threat groups that FireEye tracks and other people report, so it's being used in the wild. And just last week, I was lucky enough on Friday, thinking I would take Friday off before my trip, somebody dropped a new lateral spread technique using Decom. So I got to spend my entire day off researching and making sure my presentation wasn't a giant lie. So kind of looking back while we're here, this is going to be a quick one. I'll let it run a couple times. Essentially, attackers using command line tools, PowerShell notably, or just their own native applications, they can leverage a protocol called Decom to cause command execution on a remote system. The entire interaction on the network will happen via Decom, a normal Windows protocol that's been built in since early days of Windows. Very few people think it odd. You'll note that when this slide right here, the top of the screen here is Bro, IDS, running, capturing all the SMB RPC. And the bottom part of the screen is Suricata with a standard rule set. What you'll hopefully see is that Suricata doesn't throw any alerts by common lateral spread techniques that have been documented for a couple of years. And Bro produces really nothing of any value. So if you look at all the log output here, you see one called a function and then a whole bunch of unknowns. They're literally labeled unknown. And what we'll come to find out later is these are actually incorrectly parsed, in fact. So it's mislabeling events. So people are not really able to trust their defensive tools for attack techniques like this. Again, it's been abused by adversaries, and everyone talks about the endpoint. That's because endpoint has been all the rage lately, with all the different tools coming out, both paid and public. But it's important that we have a balanced approach. And so this is going to be solely focused pretty much on the network side of this. So kind of diving in on a 101, these are the books where we learn this. We read a couple of these. Note that these are all older than the partner I worked on this presentation with. These books are all like 1993, 97. The guy I worked on this with was born in like 2004, I think, or something. So this material is significantly dated. It's not updated. It's not well resourced. The internet is not maintaining good documentation on Decom. It was extremely hard. It's taken months to kind of learn and get to this point where we are. So what is COM? So before we can talk about Decom, we have to talk about COM. COM is essentially a language-independent model to expose application functionality inside of a computer. So if a particular application wants to allow you to, I don't know, programmatically create a Word document, you can create a COM object to enable that. The code, the compiled code or the element is what's called a component or an object, so you'll hear me kind of use those interchangeably. Components or objects are identified by class IDs, which represent, it's a unique identifier which represents the particular object being used. This will be important when we start to talk about indicators of this use. Components are typically registered on a system, meaning that they have to go through a registration process. The system has to know they exist. Big bold on typically, there's been a little bit of research lately to show registration-free COM using ActiveX and a couple other components. But for the most part, these are, attackers are going to abuse things that are registered on the system and present. And they usually implement one or more interfaces, and that's a magic word, so we're going to dive in a little bit more. So what specifically is a COM interface? It's a specific piece of functionality that's going to be exposed for use. And so what that means is if you are familiar with programming styles, an interface is something you implement or extend to get common functionality. So there are a whole bunch of common COM, quote-unquote, interfaces which have normal functionality that you can basically extend in your application. An example would be IDispatch. So if a COM object extends the IDispatch interface, it'll automatically inherit all of the stuff that COM allows you to do automation or dynamic casting. So you'll note on the window on the right, when we look at an example object, like MMC20, you can see that some of these interfaces are in fact implemented, like IDispatch, IUnknown. And these are things that you'll see get used over the network. So progressing on to Decom, which is the distributed network version of COM. It's basically what COM looks like on the network. It's good to note that this is a protocol that rides on top of RPC. So a lot of the interchange will start with RPC, and calls familiar if you're familiar with RPC, and then dive down into very specific response and request structures called PDUs for Decom. And so you'll kind of see an intermix. You'll saw that Bro's RPC parser picked out like one or two things that looked familiar, and then all the unknowns was all the Decom stuff that it's not really familiar with. In this case, a client can be practically blind. So a client does not need to know the functionality or really how to use it. They can instantiate Decom objects and then explore them, get help, and use them with no knowledge. All the code is executed on the server. So I, as a Decom client, I am basically getting code execution on a server. So talking a little bit about what the message structure looks like, I wish there was some centralized resource when I went through this, so I tried to break this down as easy as possible. Essentially, all of Decom's communications are going to start with some sort of RPC bind or what's called an alter context. These two function calls allow a particular client to attach to an interface. So again, if we're talking about IDispatch, there will be a bind or an alter context which announces I'm attaching to the IDispatch interface, which is where all my messages are going to go to. It's a way that they can do asynchronous communications and still track what interface is being involved. All of the messages that follow the specific PDUs will be in a very common format, so they should be very structured. The request will always have what's called a this structure. Whoever named these like get extra bonus points. And the response will be that. So there's a this and a that. It's really clever. And then following the this and that, there are going to be the arguments that are passed as inputs or outputs. So there's going to be either input arguments or return arguments coming back in these structures. In every Decom message, we should be able to identify the this and that structure. So it's very important when you start looking on the wire, what you're looking for is to kind of pick that out as an anchor point. So let's dive in on how bad guys have been using this. This is the fun part, the sexy part of this talk. It's short. So this talk, Decom is used really across the life cycle. So there's, you might have heard of a lot of these different techniques. There's a common set of researchers that have been heavily focused on this. But essentially, across the life cycle, primarily in these phases, so code execution, lateral movement, and persistence, there are a number of different techniques that use COM. The reason I love this as a red teamer or as an attacker is because it's so legacy that it's not well documented, and pretty much everyone just trusts it's safe because it's been around so long, and there's really nothing that inspects into it. So what options do you have? You're not just going to outright block it. God forbid you kill like a line of business application or access to a big SCADA environment. The other thing is the host and network indicators, because the tools don't really parse them, they can vary heavily. It's a very dynamic protocol. So you'll see in lateral movement, we're going to dive in on this specifically, but in some of the neat ones to look at, I would say, is people are familiar with like SCT scripts or COM scriptlets. COM hijacking has been around for years as a persistence technique. Matt and Casey document this very well on the endpoint side in this link. So take a look at this presentation. It kind of goes into a lot of the endpoint-focused parts of these techniques. So how do attackers find COM objects to abuse? Like what inspired them? What made them go look at a particular object to use for a lateral movement? The key thing they really want to look for is things that execute code. Microsoft is full of binaries and things that just allow you to compile or execute code. It's extremely common. And so it's kind of a focal point for researchers. Let me find every way I can spawn a program inside Windows. Another key piece of this is objects that have no explicit launch permission. What that means is it falls back to the Windows default. Windows default launch permission is for administrators to be able to launch them remotely. So if you're an admin, you gain access in an environment, you escalate, these COM objects by default are at your disposal. So it's a feature, not a flaw, don't worry. It's supposed to be there. There are many different tools you can explore COM classes. One of my favorite was watching Matt Nelson back in the day. I used to work with this young kid, and he would just sit in the registry and just like manually scroll through the registry and click on things. I'm like, there's a better way to do this. Like, there's commands and scripting languages and things you could use, but he found a number of these just by spending hours digging through the registry and looking at weird things that he didn't know existed. It's kind of an eccentric researcher brain right there. All of these applications match this spec. So some of you might recognize these icons. They're probably deployed on your enterprise computers. And all of them expose code execution functionality and have no explicit launch permission set, which means administrators can use them. So by installing Office, you're enabling this technique we're going to show and talk about. So I skipped one. Let me step back a little bit. So talking about finding a demo, this is the component snap-in of Windows. You'll see when we come into the component snap-in, administrators, in fact, is allowed default launch by remote. So this is a way you can check that. It's the default fallback. Coming into a tool called OLEview, we can basically search COM objects, and we can use a Python syntax. So we can say, show me all COM objects that have no launch permission defined. And you could scroll through all these and look at each one. I'm going to skip to the one I know is interesting, MFC application. You can see here that this COM object has an app ID, no explicit launch permission, has a class ID that we can then use to instantiate. So I'm going to come over to my window. I'm just going to do a quick instantiation of this, and you'll see I'll be able to explore. So I basically have an MMC snap-in COM object that has a document property, which has a whole bunch of sub-properties, and eventually when we get down to the interesting stuff, you'll find that we have a command called execute shell command. Not interesting at all to look at. So kind of weaponizing that now, we take the MMC 2.0 application and we do a get type, which essentially resolves the class ID for us. I'm going to run that. Note that I'm using PowerShell here, but this could be done entirely without PowerShell as well. PowerShell is just an easy way to make this demo show. And then I'm going to create an instance of it, which means I'm going to actually run the program and get a pointer back to the object itself, and then I'm going to tell it to run a program. It's just this easy. This is, again, built into Windows and calculator launch. Yay. Over the network, this is entirely Decom. So this is all a native Windows protocol, and nothing really super suspicious or sticks out here. In fact, most tools don't parse it. One more for you, in case you want to be a little bit more sophisticated, you don't want to just spawn programs. In this case, we're going to use Microsoft Excel. So that class ID represents Microsoft Excel. We're going to create an instance of it, and then we're going to load a DLL. So we're going to force Excel to load a malicious DLL from disk. So this is no longer spawning any secondary code. I'm loading a DLL into Excel's program space. And that DLL was planted by me. Notice it's not an actual sneaky location. Like, don't plant your malicious DLLs in the C drive if you're a red teamer. But it works well for the demo. You note that this is supposed to be loading an Excel snap-in or add-in object, and my DLL is just like a standard run main DLL. It's nothing fancy, and it just works. Like, Excel doesn't care. It kicks off execution. It doesn't validate that it's an actual snap-in or library. So let's look at what this looks like. For me, I've used all these techniques for years, and when I converted over to the blue team side, I was frankly utterly amazed that nothing found it. So I wanted to dive in. What we're going to basically walk through is what we call, or I work with a detection process. So it's basically kind of a measured process of taking a behavior technique and breaking it down. Maybe this is useful for you if you work in detection or in a SOC and you do this kind of research. We're going to focus on 2 key steps here and kind of break them down, but note that there's a whole bunch of other steps that are involved in real-world detection operations, like, I don't know, actually building indicators and maintaining them over the long term, which is the hard part of this life. So let's walk through what exactly happened on that behavior. So you'll remember that we started by instantiating the object. So this is what's called in comms language as activation. During activation on the wire, there's a number of different things that occur. We're going to break those down in a second. But essentially what happens during this stage is an object is created, a process is started, and the pointer is passed over the network back to the client. And then we'll have an optional set of operations that may or may not occur. These operations are what are called type operations, and they're used to enable a user to explore the comm object. So if you remember when I was in my little PowerShell window and like exploring the MMC object, and I was getting a list of all the functions and properties, that's done via type operations. So you'll only really see these if a user is manually interacting with the object, which can be a cool note to know whether the attacker is interactive or whether this is programmatic. And the final step will be execution. So the attacker will then call a specific function, which allows them to execute code or load code in the environment. So diving a tiny bit deeper, this is what the activation phase actually looks like on the wire. So if you were to PCAP this, these are kind of calls that you're going to see. And kind of if you were to trace on the system, these are the specific comm interfaces that are going to get hit during activation. We dug through each of these. This could be a rabbit hole in itself. You could spend probably weeks just trying to understand all of these calls. We kind of want to highlight or dive in on one specific one. So as we step through these, we're going to show you pretty PCAP and bytes, and the reason for that is mainly just to highlight what we found. Again, this protocol was fairly undocumented. So the function that we highlighted as the most important was the function called remote get class object. And during this, the client will pass a particular class ID, which identifies the Decom object, that it wants to get a pointer to, it wants to activate. So the class ID makes a really great indicator. It should stick out for you, which is why this is so important. You'll note that when we loaded Wireshark, it didn't actually parse any of this. It just said stub data and gave us a giant byte string. So that was relatively unhelpful. But the way we found this is by literally control-Fing in Wireshark for a class ID, like wondering which packets include that indicator. You'll see that we were able to parse out this class ID, this fancy GUID, which then if you do a Google search, you'll find it ties to the application object of MMC. It sticks out like a sore thumb on the MSDN documentation. So if we were to find this in the wild, you have a class ID, what do you do with it? Just go to Google. Generally, the big ones will be very well documented. The next part of the iType info operations. So there are 3 main functions that we saw getting used. There's actually like, I think, 8 or 10 total, but we really want to highlight these 3. The first one is get function description. This is essentially used to resolve an ordinal or like a single identifier to the actual member ID, which is a unique identifier for that function. Again, we're all about indicators. We want to pick out what we're able to use to identify what's going on. The next step is get names, which is where the client will actually resolve a member ID that I got from the first one to a name. So a human readable text string that is then passed back. This is how I allow external exploration of the object. And the final one, which is really neat, is get documentation. So if you want the help docs, if you want to do like get help in PowerShell on a particular comm object, that's all handled via a decom function called get documentation. And it literally passes in clear text the entire doc string. So it can be pretty interesting to see over the wire and explore. This is what all of those calls look like in Wireshark. Again, I hope that you can see that they are all generic. None of them are parsed. None of them are typed or identified. They just identify as DCERPC request response with like an interface ID. It's like the least useful parse of Wireshark I've seen. We've seen this used in the wild, and we actually got PCAP, and this is how we started down this road. As we went in and we're like, this is not helpful. I need to understand what's going on here. And so we're going to come back to this and how we can work to fix this. Got some copy slides here. The last piece is IDispatch invoke. So This is the execution phase. This is where the client actually tells the COM object on the IDispatch interface that it wants to invoke a function. You'll note that, again, in clear text, the function arguments are passed, so you can see the Unicode string there at the bottom for Windows calc.exe. So this is where, if you were to see this, you could know what was being spawned, and you could trace it back to what specific function was being used based on the member ID and the get names. So take a breath of fresh air, no more packet bytes for a while. The next step that we kind of look at is defining criteria. So within detection engineering, detection seems very magic to people. It's like, how do I got to do this magic behavioral analysis and AI and machine learning models, and it's going to magically pop out a bad guy. But 9 times out of 10, it's not that complicated. It's a simple equation. You'll have things that definitely are used by bad guys, aka strict criteria. It's required for the technique to exist. Then you'll have loose criteria, which are things that sometimes might be present if they exist. And you have exclusion criteria. So you have things that should never be there if they exist, or things you don't care about. If you just make a little simple equation out of that, so take all your strict criteria and them together, and take all your loose criteria and OR them together, take your exclusion criteria and not them, you essentially have a detection. So this is kind of an equation for detecting behaviors and breaking down particular attack chains into these criteria. For us, when we look at this, we break down strict. So essentially what was common across all of the different cases we looked at this, there was always an activation, has to be an activation for the Decom object to get mapped, which means that that remote get class object or co-create instance, another case, will always be there. What this allows us to do is that's a very strict key piece of our detection. The next piece is some method of initiating execution. This could be via the IDispatch we talked about. This could be via some other COM load method that's used. But those two key pieces have to be there. When we dive in on loose, you'll see a lot of the indicators are interchangeable. So we can't base our detection strictly on class ID unless we know all of the known bads. We can't base our detection strictly on like the presence of I-type info because that might not be there if a user's not exploring, and so on. So let's actually start talking about the NSM capabilities, or what we can actually do in real life to make this happen. So this is what we call the detection spectrum. Again, a little bit more detection 101 stuff here. A lot of people, again, are quick to rush to behavioral detection without understanding where it falls. Really, there's a number of different kinds of detection. There's atomic indicators, which everyone kind of bashes on, but sometimes they're the most useful. So like, maybe not an IP address, but a domain name, like, if it's bad, it's bad. Maybe we should just go look for domain name. Maybe it's actually that simple. A hash, another one. Obviously, they're weak. And so when we start going down the line of all the different properties or characteristics of these, I consider it weak or fragile because the attacker can easily change it. But note that it's very high confidence. And then we can look at more event-based indicators or behavioral detection with machine learning and modeling. And we kind of get to a more robust state, but usually lower confidence. You start to get a lot of false positives and requirements for tuning and learning and training, and it gets very complicated very fast. In an ideal world, you deploy lots of these different things across the spectrum. You don't rely on one. You don't just have behavioral. You have behavioral, you have some simple event metadata-based ones, and you have atomic indicators. You do use like threat intel atomic indicator feeds, and you really get as much coverage as possible. So imagine this dotted line is our attack surface. This is all the different ways that you can run this class of attack, decom lateral spread. And then these are all the different methods of doing this. So these are all the different class IDs and ways to instantiate objects and ways to execute functions. Our goal as defenders and detection engineers is to basically overlay methods, different detections across the spectrum that allow us to cover as much of this attack surface as possible. Note that I always leave methods outside the circles because it's just not realistic to find every single attack of every class of technique. I'm a realist. I was a red teamer for a while. I tend to be paranoid. So you'll also note that there are cases where there is overlap. So like the method in the middle where it's overlapping on 3 different detections. That's beautiful because when you start getting things that hit on multiple detections, it increases the confidence in clustering of that detection. So it could be more meaningful for you when you start looking at them. So let's talk NSM. We'll start by looking at the kind of 3 generic techniques that most companies employ NSM-wise. There's kind of 3 generic ways. One, there's rule-based IDS. So this is things like Suricata or Snort or paid solutions that I won't stand up here and talk about. These are very good in that they provide high confidence alerting if the signatures are good. Key, very big star. Signatures are important. But they lack context. And generally, these are only for known bad. So you have to know something is an attack technique before you'll have a signature for it. And what that means is, so you can't be very generic. It's hard to get generic and still be fruitful. Then you have metadata extraction. These are things like Bro IDS is a really good example of that. We'll talk about it a little bit more. But this inspects traffic and extracts relevant indicators from the traffic. So this isn't capturing all traffic at all time. It's not just giving you alerts. It's giving you telemetry. It's a common phrase for it. And this enables things like time series analysis and outlier detection and other slightly more advanced techniques of identifying bad stuff. Note the purpose of metadata extraction is not purely alerting. It's also, you start getting into a forensics element of being able to watch what happened in an environment. And then the last one's full content, or PCAP. So this can be very tough to scale unless you have like data centers worth of disk arrays to like store a Fortune 1 or 2 company's PCAP all the time. But it can be very useful. I mean, frankly, as a network nerd, like PCAP is generally always very, very good. I want some method of getting PCAP on demand at the bare minimum. And that allows me to dive deep when I need to. Usually this PCAP will be paired with like some method of indexing the metadata. So someone will collect all the PCAP, but like PCAP's hard to use for a SOC. So how does PCAP get used? It gets indexed and it becomes metadata inside of a SIM. Very similar to the number 2 part, metadata extraction. So let's look at how we can actually start detecting decom in these 3 techniques. We'll start with an IDS signature. So this is an example signature that when we were looking into this research, we actually deployed across our base and started to use in production environments. And this is, again, there was no prior work done in IDS for these decom objects, so kind of starting fresh. Breaking the pieces apart, essentially we're looking for the particular op number. So 03 is a particular op number for a DC RPC remote kit class object. So I'm specifically looking for a remote kit class object. My favorite is the meow signature. Super cool. I have no idea why it's in decom. It's common in decom for certain stages of the things. The packets literally meow at each other. So this is a perfect placement for a GIF if I had sound, but decided not to go that route. And then the last stage on the big piece is the class ID. So essentially, I can create a fairly well-tuned IDS signature to look for instantiations of particular decom classes. And if I can get an okay exhaustive list of decom objects, I can start detecting decom lateral movement. I'll put the caveat that you need to have an IDS like looking at internal traffic, east-west. And that isn't always common, but it's a really good, this is really good justification for those who are looking for it as to why deploy network tools internally. The next piece we'll talk about is metadata extraction. So we're going to focus on Bro IDS. It's the open source capability that allows this, and a lot of products are built on top of it, and a lot of companies build on top of it for homegrown solutions. There are 3 key pieces you need to understand for Bro IDS to start wondering how we can detect decom. One is binpack. So binpack is the Bro IDS element that allows you to define parsers. It's essentially a language that you can define structures to parse out of the network. The next step is events. So when a binpack signature matches, it'll cause an event to fire. So there's a whole eventing engine inside of Bro. And then when an event fires, it's handled by an event handler, which is a script. So scripts are written dynamically. They are meant to consume network events and do things with them. They can do things like output events. They can do some basic detection and analysis. Essentially, you can do anything you can do in like languages like C, which is Bro's under the hood. So what's wrong with Bro? Why did we get all those unknowns? That was my first question, is like, Bro's usually really good. The parsers are very, they lean forward. They're usually out really early. And decom's been around so long, like, why isn't parsing? Well, I went to the Bro source code, and you'll see this picture. Like, 2 of the biggest functions that are important for DC RPC are literally just commented out in Bro's parser. Like the hashtags DC alter context. They're simply not even handling alter context in Bro's current RPC parser. Which means that anytime an alter context is used to change the interface that you're looking at or using calls to, Bro won't see it. And so all of the calls after that alter context are actually mislabeled. They're false events. They're not helpful. They could cause alerts when they don't need to. It's a huge problem. So that's one of the big problems. And the other one is because Bros is an RPC parser, it's not focused strictly on decom. It doesn't parse out some of the decom-specific pieces, like the class IDs, which are really important to start to identify malicious use. So those are the kind of key pieces that we identified and wanted to set out to fix a little bit. So the first piece, and the piece we were able to get done in relatively short form and present to you today, was the ability to parse class IDs. So essentially what we had to do is we had to go into Bros underlying source code and modify the ability to parse the full DCE RPC stub. So you'll note that when PCAP we showed you that stub data, essentially it's all the decom specific stuff of the RPC message. We want to pass that to the event handler. So I can do event handler logic to say if this is a particular operation, like remote get class object, I can extract the CLS ID and log it. That allows us to start to get those indicators down on paper so that we can do forensics and trace what is going on. This is the Bro script I use. This is super ugly. I have red disclaimers here. You'll note that this is still like beta. This is internal work being done. We're actually looking to try to submit a pull request to Bro to fix up all of this decom work, but it's a lot longer of a process. So this is beta. This is running. It works in production. I've tested this. Essentially what this does is look for the two different methods of doing activation, remote get class object and remote create instance, and parse out class IDs and log them in the RPC log. And we're going to get an image of that soon. So let's look at that new telemetry. I'm going to do the same technique. I'm going to do an MMC2O application. I'm going to create the instance. I'm going to spawn a command. And when I come over to my defensive tools, so yay, calculator. When I come over to my defensive tools, you'll see I have some added stuff. Instead of, I now have the class ID of the object that was ran. So that class ID tracks to MMC. I also have a Suricata signature that fired. So no longer is my telemetry completely useless. I have the basics. I have enough to do some forensic analysis and say what CLOM was used, and I have enough to do some basic alerting when this stuff is firing off. So again, it's a little bit better. There's still a lot of room to grow. We still haven't fixed the full decom part. So that's what we're working on internally now to add back to Bro. But getting this has been enough for us. So we see red teams all the time in our customer environments doing this stuff. This is like their favorite technique because they think it's going under the radar. And with this stuff been deployed internally, we've had success a number of times now catching. So what do you do with this data? So we have telemetry. That's not the end of the pipe. So I like getting creative. I like doing multiple forms of detection. Here are 4 example detections that you could deploy or build with this telemetry. So first, the simplest, we could just build detections around known bad decom. So like I have 8 or 10 objects which red teamers have put out blogs on. Pretty guaranteed that threat actors will follow the red teamers. Fun fact, like APT32, they pretty much are on a 6-week lag time to all of the blogs that the red team folks put out. So like we'll see a red teamer blog and 6 weeks later APT32 will use it. Like we see it in the wild in customer environments. And so if you can just follow and get that level of coverage, you're 75% of the way there. We could also look for behavioral indicators of when it's being instantiated. So we could actually trace the IDispatch invoke calls, log the member IDs, and track what type of functions those go back to. So in addition to just looking for bad objects, we can actually look for bad use of bad objects. This will help reduce false positives because you won't worry about things where objects are getting used normally. We could do fun things like anomaly detection or novelty detection on decom. So I don't know if 2 workstations who have never talked before begin talking over decom using the MMC object to spawn calculator. Like, that should stand out. That's a needle. It's in a haystack, but it's a big needle that should like be red in the haystack of black. So it should be very easy to pick out. Generally, the decom is going to be very standard between certain systems, like line of business applications. And then we could, this is my favorite, is actually modeling decom to identify interactive use of when a human is doing the decom. So basically create a statistical model to look at normal use of I-type info versus like adversary use of I-type info operations, and being able to pick out like when an adversary is exploring objects that normal people shouldn't explore in ways they shouldn't do. And this is a lot more sophisticated. It would take a lot of training data, which is hard to come by. But this is a route that we really want to go down and check out. So I've ignored PCAP up till now, and primarily because we're focused on detection. But when we get to forensics, PCAP is very, very important. Even if you don't have a tool constantly running PCAP, during an incident response, it's pretty guaranteed that you're going to collect PCAP from compromised hosts. The most common tool that people use to look at PCAP is Wireshark. There's other things like CloudShark for the enterprise versions, or CyberChef, which is an analysis tool. But Wireshark's by far market prevalence. Wireshark's built on top of two key concepts. So there's dissectors, which are the inline C code ways of analyzing protocols and parsing them out. So this is written in C, it's hard-coded inside the Wireshark source code, and you have to rebuild Wireshark to use it. And then there's plugins, which enable you to do dissection, but it's written in Lua, and it's a little bit more dynamic. You don't have to rebuild Wireshark every time you deploy a plugin. Now, parts of Decom were handled in Wireshark, parts. So you'll see like 1 or 2 functions and operations implemented, but for the most part, there's a huge blank slate in Wireshark that just wasn't handled properly. Those are all those generic PDUs and request and response structures that are left out here. There are also several endpoints and operations that lack dissection. So you'll note that the remote get class object was written, it recognized it, it dissected it, but it didn't do any further dissection besides pulling the data, which again isn't very helpful. So what we wanted to focus on is contributing back to Wireshark to build out all of the modern Decom protocols we saw used. So we're going to be submitting a pull request in a couple days to Wireshark to add all of this Decom stuff and get it into the tool for use. The key things we did is we added references to new dissectors for all the different interfaces that we didn't have before. We built out a specific packet-decom-typeinfo, so we implemented the entire iTypeInfo interface in Wireshark, and we added some things to System Activator to allow IDispatch to work. How many people have done protocol RE before in networking? Okay, I see a couple hands. This is a monster, and it's truly an art. It's less than a science. It's kind of like solving like 50,000-piece jigsaw puzzle, where you have to find edges, but it takes you like hours to get edges. But if you get those edges, you really can start trucking along. It's very, very similar to that. So I have some tips for you based on all the work we did here. If you ever have to do this, I hope you heed this advice. I think it's useful. So leverage existing dissectors. One of the biggest learning gaps is actually trying to figure out how Wireshark works and how the dissectors work. Like, what are the functions you have at your disposal to do dissection? How does the tree structure work? But if you just go read some other dissectors that you understand, like, I don't know, go read the FTP dissector. You understand the protocol. It's a very simple one. And you can go ahead and figure out all the different functionality there and then start working. Fun fact, a huge part of our Decom stuff is like copy-paste of other RPC dissectors, because a lot of the functionality works and works great. And it was written by better C coders than me. So it's less likely that I'm implementing like a buffer overflow in Wireshark, which is important. And then use official documentation. RFCs are a really great step. If you've ever read an RFC, I highly encourage it. It's good bedtime material. You'll get a good sleep afterwards, but very useful for network folks. Even better for Decom specifically, MSDN. So pretty much all of the Decom functionality is sort of documented on MSDN. It's documented like 15 different times in different places. So you'll go to like one page where it's documented, and it's different than the other way it's documented. So you have to kind of sort out what year it was published and how likely it is the author knew what they were talking about, which is always a fun thing to do when you're trying to RE. I like to encourage people to use multiple variations of the attack. Don't ever just run one version of the attack and try to RE it. Like, get 5 side by side so you can start to identify common elements. I like to identify high confidence markers. So specifically in the terms of Decom, this is our this and that structure. By identifying the this and that structure inside of the request responses, we know where the anchors are going to be for the inputs and outputs. And we can start working through those inputs and outputs sequentially. This could also be like the end of the packet. Sometimes the end of the packet is your best marker. Start from the end where you know the last thing is going to be and start working backwards to identify all the elements. I'd like to highlight there's no guarantee that other people did it right. There's no guarantee that other people understand the protocol better than you. That was a bad assumption that we spun our wheels on for a long time. We're reading blogs on Decom thinking that if we just trust this guy, like, it'll lead us down the right way. And weeks go by, and he was actually completely wrong in his documentation. So you have to trust but verify the work that you're doing and have a little confidence that you know how to read an MSDN spec and know what it's doing. Little hint, after writing a whole bunch of these Decom parsers, we found this cool tool called PIDL, which simply takes an interface definition in Decom and converts it to a dissector for you. So I have no idea why this stuff hasn't been implemented in Wireshark, because this tool does all the work. So if you ever run across like really weird stuff that you see in Decom and you want to get a dissector working pretty quick, use this tool. It can be very, very helpful. So this is what we end up with. I'm actually going to roll to a quick demo, see if it slides over. The demo is not clutch, so it's not a big deal if not, but yeah, it's okay. We'll keep going. Basically, all I wanted to show you was that we were able to get this all parsed out. So you can see in the screenshot, too, the get names response. This is the type 7, which was not previously working in Decom. It was just saying like random weird garbage. It didn't parse it out. You'll see that it actually tells us this is a get name response. It parses the that structure. It gives us all the names that it found. So we can do a full forensic dissection and filtering now in Wireshark to kind of go through this information. This was very, very, this seems simple in this picture, but it has been extremely useful for forensic context on these attacks. Right. And now my pointer stops. So the kind of rounding out here, so I would be negligent if I didn't address some amount of endpoint detection. I'm a network nerd. I've been a couple years doing network analysis now. And in the Air Force, I did a lot of network analysis. But as a red teamer, I knew a lot about the endpoint. So the best detections are balanced, and the best approaches are balanced. They're not all network. They're not all endpoint. They're taking network and endpoint and putting them together in a common view and making use out of that data. So why is endpoint required here? Fun fact, RPC can be encrypted. In most locations, it's not yet because your domain controllers are like 15 years behind spec. And that's okay for me because I like it not encrypted. But if in future environments, like 2016 functional level and above, you're going to start seeing packet privacy enabled. So you're going to start seeing RPC details encrypted on the wire. So it's a good motivator to start thinking about endpoint detections that are reliable. Additionally, an adversary can actually force the packet privacy flag. So for you red teamers, you don't want to get inspection on Decom, you can actually enforce packet privacy on the command line. I'll note that we have had somebody do that. They force packet privacy, and that's actually an indicator because like the environment doesn't have packet privacy anywhere, and then all of a sudden one Decom connection with packet privacy stands up. Like, you know, that's not good. So sometimes the best evasions are actually the best indicators. So let's look at endpoint. The endpoint can actually be pretty damning for these attacks. If you can get command line logging, this is going to be your best bet on the endpoint for Decom. One of your best bets. It's easiest also. Decom processes that spawn will spawn underneath the Decom launch service. So it'll be an SVC host that's dedicated for Decom. And so I don't know if you have like 15 Excel objects and a Word object and an MMC object spawning over under SVC host, you have an adversary you should probably be worried about. And that adversary is probably also pretty sloppy. But you'll see on the screenshot here, you have Outlook and Excel. Outlook and Excel are both under the SVC host process. Many of the Decom objects actually don't allow you to gracefully exit. Like there's no way to shut down the Decom object gracefully. And so the adversary is going to be stuck with a running process that they won't be able to kill unless they get on the endpoint. And that's assuming a perfect adversary, which you should never assume because they have life problems too. And so a lot of times there will be these processes like hanging around for long periods of time, especially on server environments that don't get rebooted often. So if you're going like threat hunting and you're doing like process sweeps in an environment to go look for potential malicious use, hit your server environments and start looking for child processes under Decom. It's a pretty simple analytic to run. It can be pretty useful. Another fun fact is Office applications that start via COM are going to have the embedding or WAC automation flag. And these will be indications that respond purely via Decom. Note that this will happen sometimes legitimately because for some people they actually use Office as like a programmatic object in their environment. So don't necessarily go running to the CISO every time you see this. That would be bad and you could hurt your job. So we're going to wrap up. So what takeaways do I want you guys to have out of this? So there's obviously the technical takeaways. Hopefully you can take some of these detection styles, some of these Suricata signatures. You can go replicate this and get it into your environment so you're protected. There's a broader process here that I don't know if anyone caught that we kind of follow, and I follow. This is my everyday job. Basically, we take an adversary technique, I emulate it in a lab environment with lots of telemetry. I try to look for specific phases or pieces of the attack. I conduct analysis, so this can be either network or endpoint analysis, and then I take all the artifacts that I can identify to build detection. So this is detection engineering, if you've never heard of this role. It includes a little bit of red, a little bit of blue, and it's a ton of fun. And then there's the non-decom specific takeaways. So this is the idea that our mission on the blue side is to detect threats, but a lot of times we don't have the capabilities we need built in. No matter how awesome the tool is or how long it's been around or how long the attack's been around, there are going to be weaknesses and holes. And so you need to understand where your holes lie, what visibility gaps do you have, and you need to work to mock up that behavior and increase visibility in those gaps. This is an iterative process. It will take years in a real organization to continue to do this. But some of the best customers I've ever worked with on the consulting side as well as on the defensive side are folks that do regular detection testing, regular gap analysis of their telemetry and their systems to figure out what's the most likely place that they're going to get popped. So that is it for me. I should have a couple minutes at least for questions, if there are any. Sweet. Packets make people sleep. I get it. My interns sleep all the time. All right, cool. I'll be around after the con in the hallways and in the back, so feel free to connect. And it was awesome being out here. Thank you guys so much for your time and listening to me jabber on about this. Have a good day.